Welcome to Chem-Tech Laboratory Tutorial. Today we'll be looking at chemical equilibrium. Chemical equilibrium. When we talk about chemical equilibrium, we are talking about reactants reacting to form products, and products can also react to form that same reactant in a reversible reaction. So in that case, we'll say both the forward and the reverse reaction are balanced. But that does not mean that the reaction has stopped. What it only means that the reaction is still ongoing, only that the stoichiometry of the reaction is what? Balance. So in that case, we calculate for the equilibrium constant. When we say equilibrium constant, we are looking at the quotient between the products and the reactants, where we say A plus B will give us C plus D. Now, this arrow indicates that it's a reversible reaction. When it's pointing forward, we say it's forward reaction. When it's pointing backward, we say it's reverse reaction. But by the time the reaction is one full arrow, we say it's what? It's just a forward reaction, and it is an irreversible reaction. So for the sake of chemical equilibrium, the full arrow is represented as an irreversible reaction, meaning that if you are reacting A to get B, B cannot give us A, but A can only give us what? B. So this full arrow shows that it is an irreversible reaction, while the two arrows shows that it is a reversible reaction because A plus B gives C plus D, and C plus D will also give A plus B. So the value of the equilibrium constant depends only on a particular reaction and also depends on the temperature of that reaction. And this, we said, it is calculated as Kc is denoted as the equilibrium concentration of a reaction, equilibrium constant concentration of a reaction. So we do it this way so that Kc will be what? Product, concentration of the products raised to power coefficient all over concentration of the reactants raised to power the coefficient. So this is how Kc is calculated. So it therefore means that for this particular reaction, we will have C, concentration of C raised to power small letter c, concentration of D raised to power small letter d, all over concentration of B raised to power small b, and concentration of A raised to power small a. So, for example, if we have a reaction of ammonia, that is N2 plus H2 to give us NH3. So it therefore means that this will be a balanced reaction. And how will your Kc for this reaction be? For a reversible reaction, the forward reaction Kc will be NH3 raised to power 2 all over N2 and what? NH2 raised to power 3. So this is the Kc for a forward reaction. So we can put it as Kf. Then Kr, which is the reverse. The reverse meaning that this side automatically becomes the product. So it becomes N2 and H2 raised to power 3 all over NH3 raised to power 2. So this is for the reverse reaction, and this is for the forward reaction. So if we can remember that the Rate's law, which is the law of mass action, was stated that it is directly proportional to the concentration, directly proportional to the initial concentration of the reaction. So let's say the rate law for the forward becomes Kf And what will be the reactant? The reactant is N2 and H2 raised to power 3. With this, you can easily calculate the order of reaction because we say using the law of indices, where we say 1 plus 3 is equals to 4. So this is fourth order. Then the reverse reaction. The reverse is that the reactant, the product becomes the reactant. So you can represent it as what? Kr concentration NH3 raised to power 2. So this is how to represent the rate law, the law of mass action for both the forward and the reverse. So now we'll be looking at Kp. We have talked about Kc, and we said Kc is equilibrium constant for concentration. Now we'll be looking at Kp. What is Kp? Kp is also equilibrium constant for pressure. And pressure is affected by gases for gaseous compound. Now, the concentration of pure liquid and pure solid are always equal to 1. That is, if the state of the compound is in solid form or the state of the compound is in liquid form, the concentration of them are always equal to what? 1. So it means that if I say we have calcium carbonate undergoing decomposition in a closed system, it will give us calcium carbonate is solid, CO2 is a gas. Sorry, this is calcium oxide. Calcium oxide is a solid and CO2 is a gas. What will be the Kc expression for this compound? It means that in a closed system, the forward reaction for Kc will be Kc is equal to product. You know that product raised to power is coefficient all over reactant raised to power coefficient. So Kc will be equal to CaO, then CO2 all over CaCO3. But this will not be the expression of Kc because I said the concentration of a solid and of liquid is equal to 1. So that means the expression will be equal to 1 times concentration of gas all over 1, which means that Kc will now be equal to concentration of CO2. So this will be the expression for this reaction. Why? Because the concentration of solid and liquid is equal to 1. So you can do the same for reverse. When you do the same, you see for the reverse it will be 1 all over concentration of CO2. Now that takes us to the gaseous compound. How do we express the gaseous compound? We know that the rate of according to the rate of reaction of gases, the change in pressure affects the rate of what? Reaction. So it means that the gases will be represented with their partial pressure. With what? Their partial pressure. And that gives us what? Kc. And it is represented as what? PCO2. That is partial pressure of CO2. For example, we have the ammonia. Ammonia reaction is all gaseous. This is gaseous, this is gaseous, and this is gaseous. You first balance the reaction. The first thing for every reaction, you first what? Balance. And how do you represent the Kp? Because all these are gaseous compounds, that means our Kp will be equal to PNH3 raised to power 2, which is the coefficient, all over PN2 dot PH2 raised to power 3. So this is how to represent Kp, and Kp is the equilibrium constant equilibrium constant of pressure for gaseous compound. So that is how we represent Kp. Now, how do we relate Kp to Kc? We relate Kp to Kc by using the ideal gas equation. Now I'm going to show you how it is. So we're going to learn how to build a relationship between Kp and Kc. And like I said, that this relationship is based on using the ideal gas equation. And remember that the ideal gas equation is given as PV equals to nRT. PV equals to nRT. And therefore, we know that the Kp is a representation of the gaseous compound, the pressure, equilibrium constant for pressure. So making pressure the subject of the formula, we divide through by the V, the volume, which is P is equals to N over V R what? T. So the pressure of the gas is given as what? nRT over what? V. So let's assume a reaction between A to give us what? B. A reacting with itself to give us B. And we know that the equilibrium constant of this reaction is given as what? B raised to power B coefficient. Let me just put B here and A here. So B and what? Concentration of A all over A raised to power A coefficient. So this is the relationship of Kc. Now Kp, assuming the B and A is gaseous, so it means that our Kp will be, what is the partial pressure? Pb equals to Nb over V RT, because we know R is a constant and T is our absolute temperature. So the same thing, Pa for the partial pressure of A will be equal to what? Na all over V R what? T. So you see that divided through by Pa, we have Pb all over Pa equals to Nb over V RT. All this is what? Raised to power B. Then Na all over V RT raised to power what? A. So how do we simplify this? We simplify it by saying that Pb all over Pa is equals to Nb over V times what? V over Na, while RT becomes P minus A. So V is a common term, so it becomes V all over Pa equals to what? You know, the whole of this is assumed to be what? Concentration of P and concentration of A. So we put it as what? Kc RT B minus A. So we know that Pa over Pb is what? Kp. Kp, because that is how Kp is being calculated for by representing it in their partial pressure. So this is P over B, P over A, which is what? Kp. Then Kp will be equals to Kc RT P minus A. What is this P minus A? That is what? The number of moles. The number of moles. So Kp is equals to Kc RT raised to power P minus A. What is B minus A? That is the number of moles, the stoichiometry of the product and the what? Reactant. Therefore, B minus A can be represented as what? Change in N. So we can simply simplify it to be Kp equals to Kc RT raised to power beta N. So this is the relationship between the partial pressure of gas, equilibrium constant of pressure, and what? Equilibrium constant of concentration.